Hey everybody, Mr. Tannen here. I got a few questions about this assignment, particularly practice B. Number 7 here we have a word problem. Number 5, I also had a question, and number 21, among others. Some of these, like these inequalities, we'll also take a look at on Monday when we're together. But whether you did practice A or practice B, hopefully this will be a useful exercise for us to look at together. There's a little delay on my drawing pad. I don't know why. So if I have a 2e to the 3x power plus 6 equals 10, well, first thing I want to do is isolate the exponential. So I could subtract 6 from both sides. 2e to the 3x power equals 4, divide by 2 to both sides, e to the 3x equals 2. So, we now have the inverse operation that we could use. We want to get this out of there, so what I'll do is I'll take the natural log of both sides, because the natural log is base e, and since the exponential is base e, that cancels out. And I just have 3x equals the natural log of 2, so my precise answer would just be that x equals the natural log of 2 over 3. And it doesn't say, I mean, we could stop there perhaps to solve the equation, but let me take it out of my backpack here. I did bring my TI, so let's see what that turns out to be. So it's saying the power of e that gives you 2, and then dividing it by 3. Or we could just do the ln of 2 divided by 3 in my calculator. And x would be a 0.23 in this case if I'm rounding to the 100th. So that was number 5. Let's take a look at number 7. I'll do that one in red. I'm going to zoom out a bit so that we can see a bit more. So 50 grams of radium are stored in a container. The amount R in grams of radium present after T years can be modeled by this function. So it looks like the 50 is built in there as the starting amount times e to the negative. That looks like 3 zeros after the decimal for 3t. So after how many years will 20 grams of radium be present? So R is the amount of radium present after time. So I can replace R with 20, bada bing, bada boom, and I could then solve for T. Okay, nice. Now I got my logarithmic tool belt to solve this. 20 over 50, if I divide both sides, right, I'm going to need to divide that 50 out. It's not being put to the power, so I just get 2/5 or 0.4 equals e to the negative 0.00043t. Oops, little funky writing, but it's okay. Take the natural log of both sides. I'm just going to get the ln of 2 over 5 is going to be equal to this number. We got it out of there. 0.00043t divide by 0.00043 negative, sorry. And so the amount of time would be equal to this log. Maybe I'll put it in parentheses now since it's getting a little bit more complex. Divided by this funkalicious decimal. So let me go ahead and break it down on my calculator. Do you want to see how I do it? Okay, well, let's see. You can't really see my screen too well, I guess. Natural log of 2 over 5, or I could do 0.4, either one. Okay. Then that is being divided by a negative. I'm just going to type it as it is, 0.00043. Oops. Silly, Mr. Tannen. I put the T over there, even though I was just dividing to isolate the t, so enter 2130.91 if I round to the nearest hundredth. And so that would be the time in years. Wow, so it's a lot of years. OMG. 2,100. Maybe we could just round to the nearest year. 31 years. Okay, the next question is saying 75 grams of radium are stored in a different container. So the amount of grams in radium is basically the same equation, except our starting amount there, the coefficient of the exponential is 75 instead of 50. Will it take more years or fewer years for only 20 grams of radium in this container to be present compared to the answer in part A? Explain. Well, it would take more years if I am thinking correctly, because we're starting with more. The decay rate is the same, and it would end up taking much longer. I'm curious how many years it actually would be. And so it's more because we're starting with more, so it'll take longer to decay. Okay. And then the last question, I believe it was 21, which is the word problem. I hope this was a nice challenge for everybody. You had to recall some of your compound interest, and if you go to the Google interwebs, compound interest formula, we've got the final amount is the principal times the quantity of 1 plus the rate as a decimal, not a percentage, divided by the number of times interest applied per time period to that same number times t. So normally if this is months, it would be like 12, 12, and then t will be the years. So this is saying we have two accounts. We deposit 2001 that pays 2.25 annual interest, compounded monthly, and then 2000 in account B, which pays 3% annual interest compounded monthly. When is the sum of the balance in both accounts at least 5,000? So yes, there's some where you could perhaps use an inequality, right? We want to say it's at least so greater than or equal to, but if we just saw where it's equal to, we know that after any more time than that, it would be greater than. So we got 2,000 times 1 plus the rate, first rate as a decimal. Remember, move the decimal over twice. Divided by 12 to the nt power, so that'll be to the 12t power. And then my other account that's going to be added would be the same values, basically, it just has a different rate. So I'll get 1 plus 0.03 over 12 to the 12t power. Wowzers. So I look at this equation, and there's perhaps some things we could do, divide everything by 2000, but it is a little tricky because we have these two quantities that have different bases. Although the exponents are the same, what I would maybe try to do here is try to solve this by graphing. And I'm going to actually, I know I try to use the calculator, but I'm going to actually try to use Desmos just because Desmos is that much, especially if you don't initially have the correct window. So we have our one, we want to find out when it's 5,000, so we could even say like, my cursor's not showing up on my thing, so I guess I just have to say y equals 5,000, okay. We're definitely going to need to zoom out on this mamma jamma. Maybe I could even change my x-axis. Definitely want to make this above 5,000, so we'll think 6,000, and then we can make my x-axis, let's just make it from negative 5 to 20. See if that's enough. I'm not sure quite yet, but see how it looks after 20 years. We could always scroll to the right. So then my second equation, if I just graph that crazy equation I have, I'm not going to necessarily need to do any calculations, and then I do check it out, and I think I'm remembering it correctly. I could put t also. That's the nice thing about Desmos. In my handheld, I would have had to use x because it knows that as the input. Compounded monthly to the 12t. And look, it'll be after about 8.5 years. So it'll be during this 5th month. So, oh no, we could figure out exactly what month if we wanted. I don't think the answer key just asks for the decimal of years, but if we do 0.491 times 12, that tells us it's during, almost at the end of the 6th month, so at the end of June in the 9th year. Well, assuming we started it January 1st. It didn't specify, but graphing this crazy thingamajig is going to be a nice strategy for solving this one. So I know this was likely a tricky one. The sum of those two accounts would reach it after 8.491 years. And if we want to say approximately 8.5 years perhaps, let's see what the answer key had told us. Yeah, it says 8.5 years. So sum is at least $5,000 at about 8.5 years. Please comment any questions you might have, and have a great weekend, everyone. Much love.